me this opportunity of, to present my work. So today I'll be talking about finite landscape of 61-zero supergravity. And this talk is based on my recent paper last November with Kumnu Bafra and Kai Su at Harvard University. Okay, so okay, let me start with the motivation for this work. So first, in string theory, we know only finite number of supersymmetric string vector in Minkowski space. And also in math, there is a related idea proposed by Yao. He conjectured the number of Calabi-Yau manifold in each dimension is finite. As we know, this is a highly non-trivial conjecture, but quite interestingly, quite remarkably, this was proven for the Calabi-Yau manifold with elliptic vibration. So for example, the Gross first proved that the number of elliptic Calabi-Yau threefold is finite, and later in this paper, they proved the number of elliptic Calabi-Yau manifold in any dimension is finite. So all the string theory examples together with this math proof indicate that strict compactification may provide only a finite number of consistent quantum gravity theories. Okay. And these ideas naturally lead to the conjecture called the finiteness conjecture proposed by Bafra, Douglas, and Acharya and Douglas. And they said that set of consistent quantum gravity vector for a given dimension would be finite. And there isn't a bound on the number of messless fields. And for the series with the largest supersymmetries, and these finiteness conjectures are kind of well established. So for example, the series with the 32 supersymmetries are almost uniquely determined by supersymmetry. So they are essentially toroidal compactifications of M theory or 2B theory. So the finiteness conjectures are trivially satisfied for the series with the 32 supercharges. And for the series with the 16 supersymmetries, we can actually use the unitarity of the string proofs and various sample and argument to show the number of quantum gravity theory is also finite. And in fact, we can argue that rank of gauge algebra, which determine the effective field theory and low energy uniquely, is bounded by 26 minus D for the given dimension D. So for example, the 4D n equal 4 super Yang-Mills series is consistent for arbitrary gauge algebras without gravity, but it cannot consistently couple to quantum gravity when the rank of gauge group is bigger than 22. So this finiteness conjecture provides very clear distinction between the quantum gravity and ordinary field series without gravity. And this also brings us a related conjecture, so-called the string Lampos principle or string universality. It claims that all consistent quantum gravity theories arise from string theory. So it's saying that quantum gravity landscapes exactly agrees with the string landscape. So again, for the series with the larger supercharges, this principle, this conjecture holds very nicely. For example, in 10D with the 16 supercharges, gauge algebras are strictly constrained by the anomaly cancellation. So it allows only the following 4 gauge algebras. As we know, first 2 gauge algebras had realization in string theory. So actually the 10D heterotic string theory can have these 2 gauge algebras. On the other hand, these latter 2 gauge algebras, including abelian factors, have no realizations in string theory. But in these two papers, it was shown that these 2 gauge algebras with abelian factors are indeed in the swampland. So the string Lampos principle actually holds in 10 dimensions with 16 supercharges. However, it's not easy to generalize this idea to lower dimensions. But nevertheless, there are many recent works showing that the string Lampos principle holds at least in 90 and 8 dimensions in terms of the length of the gauge algebras. Okay, then we can ask the following question. So can you establish finiteness conjecture and string universality in the series in lower dimensions with fewer supercharges? For example, the series with 8 supercharges. And this is a highly challenging problem, but today I'll provide very strong evidence supporting these conjectures. So for this, we shall focus on 61-zero supergravity in Minkowski space. As we know, this the Shakti shield is special with several reasons. For example, the Shakti is the highest dimension with A supercharges. So if you are interested in these conjectures in low supersymmetry cases, this Shakti shield is a good starting point. And these are chiral series, so the anomaly cancellation provide very strong constraint on the structure of these 6010 series. And we can also engineer this 6010 supergravity series using F theory compacted by an elliptic Calabi-Yau threefold. So this is called the geometric engineering investigated in these papers. And in this geometric construction, the low energy physics is determined by the properties, geometric properties of this elliptic threefold. And as I mentioned, it's proven that number of elliptic Calabi-Yau threefold is finite. So this means we have only finite number of Shakti series from the F theory. So the finiteness conjecture holds at least for the Shakti F theory models. There are also many attempts to show these finiteness conjectures from the effective field theory perspective. So for example, in this series of papers by Taylor and his collaborators, they proved that there are only finite set of allowed gauge groups and also non-abelian representations when the number of tensor in Shakti is less than 9. So actually, we still need more general proof for the cases with a large number of tensors and also generic representations for the abelian gauge groups. Indeed, there are many infinite families of anomaly-free series, in particular when the number of tensors is bigger than or equal to 9, as discovered in these papers. And some of these are actually ruled out by using the unitarity of the string proof as discussed in these papers. But we still have many other infinite families of anomaly-free supergravity series which are not killed by currently known constraints. So it's unclear whether these finiteness conjectures hold in Shakti with H supercharges. Regarding this problem, today I'll provide the bottom-up argument to show that number of massless field in Shakti 10 supergravity has upper bound, and the series saturating this bound are realized in string theory. Okay. So our approach is based on the following two assumptions. So our first assumption is that we have tensionless BPS strings at every point on the boundary of the tensor moduli space, including asymptotic boundaries. So in Calabi-Yau geometry, actually this assumption corresponded to a trivial statement saying that Keller cone of the base B of elliptic vibration is dual to Morricone. So all the F-theory models actually trivially satisfy this assumption. But from field theory perspective, it seems that this assumption is rather strong, but actually not, because the only mechanism currently we know that define the boundary of the tensor moduli space without breaking in 6 dimensions is putting some extra light degrees of freedom at the boundary, which is associated to the existence of the local CFT point or little string series or critical string. And all of them has the tensionless BPS strings at the location of the boundary. So I believe this assumption is a reasonable assumption. So this is the tensor moduli space. So every boundary, we expect to have the BPS tensionless string. So this is our first assumption. Then our second assumption is the classification of 60 SCFTs and little string series, which are extensively studied in these many papers, is complete. Okay. Actually, this classification studied in these papers covers all the known constructions of 60 SCFTs and little string series, including frame construction and geometric engineering, and as well as the gauge theoretic constructions. So I also believe this assumption is reasonable. So based on these two assumptions, today I will show you kind of finiteness of the 60 10 supergravity series. Okay, any question?
Maybe a quick question is,
Okay.
are you going to include the frozen 60 SCFTs?
Yes, yes.
Okay. Just making sure.
Yeah, so we also discuss frozen ones. So they are constructed by, for example, using the gauge theory, particular gauge group and method representation. So almost end of this talk, I'll briefly mention about frozen singularities. And all our discussion actually covers the cases with the frozen singularities. Thank you. Any other question? Okay, so this is my plan for this talk. I'll begin with a brief review on 61 supergravity series. Then I'll explain some key properties of the tensor moduli space and BPS strings. Then next, using these properties, I'll show you how to prove the finiteness of the 61 supergravity series. And then I present the exact bound on the number of Messerschmitt field and show you that these bounds are saturated by concrete geometric models in F-theory. Okay, let me begin with the introduction to 61 supergravity. And we know there are 4 types of massless supermultiplets. And first one is gravity multiplet, which contains the graviton G mu and self-dual two-form field and gravitino. And also in 60, there is a particular multiplet called the tensor multiplet, which consists of the anti-self-dual two-form field and a real scalar field, which we call J. Then the vacuum expectation values of this scalar field parameterize the moduli space, which we call tensor moduli space. And essentially, we are interested in the physics on this tensor moduli space. Furthermore, we have vector and hypermultiplets, and we denote the number of tensor, vector, and hypermultiplets by T, V, and H, respectively. And there are massless chiral fields in this series, such as a two-form tensor field and gravitino and metafermions, and they contribute to the gauge and gravitation anomalies. And these anomalies are captured by this one box diagram in 6 dimensions with 4 external gauge and gravitational sources. Then the consistency of the low energy theory requires that this anomaly must be cancelled. We can use the 6-degree Green-Schwarz mechanism to cancel this anomaly, which add this Green-Schwarz term to the classical action. Then this addition of this action induced the additional anomaly contribution mediated by this two-form tensor field. Then this additional anomaly can cancel the anomaly from this one box diagram. More precisely, such anomaly can be cancelled if the anomaly polynomial factorized in this way. So one box diagram provides anomaly A form. So this is anomaly polynomial. So if this A form is factorized as a product of 2 4 forms, then we can use the Green-Schwarz mechanism to cancel the one anomaly. Here, omega is the tensor intersection form with the signature 1, T, and this 4 form is appearing in this factorization expression is proportional to the curvature square term and also field strength square. And coefficient B0 and Bi, which we call the anomaly vector, are living in R1, T space. So the condition for such factorizations are as follows. So we have very complicated many conditions. But once we find the solution to these conditions for these anomaly vectors, together with the gauge algebra and method representations, then such the one anomaly factorizes, and we can cancel it by using Green-Schwarz mechanism. So every consistent 60 supergravity theory satisfied all these conditions. So first condition is called gravitation anomaly cancellation condition. And this condition will play a very crucial role when we discuss the finiteness of the number of Messerschmitt field, which I will discuss in detail later. Okay. So it gives the relation between number of hyper, vector, and tensor multiplets. Okay, let me explain the tensor moduli space. That is the two-dimensional coset space of this form, parameterized by the scalar field J in the tensor multiplet. Then the consistency of the low energy theory on the tensor moduli space requires the following 3 positivity conditions for this moduli vector J. Okay, so first condition is J square positive. This condition is required to guarantee the metric positivity on the tensor moduli space. Is for the positive gauge coupling for the gauge algebra GI associated to this anomaly vector BI. And for this last positivity condition, we can use the consistency of the compactification of 60 theory on K3 while preserving supersymmetry. But there are also many other arguments showing these positivity conditions in these papers. In F theory, this scalar field corresponds to the Kähler form J on the base of the elliptic vibration, and these three positivity conditions are required to define positive definite Kähler cone of the base. So all the F theory models satisfy these positivity conditions. And also you can find the map between the field theory data and the geometric data. For example, number of tensor which we denote by T is the same as H11 of the base. And this anomaly vector BI corresponds to the holomorphic two-cycle CI, supporting the gauge algebra GI associated to this BI. And B0 is the anti-canonical class of the base B. Okay, on the tensor moduli space, we have a particular BPS object called the BPS strings, and they have half BPS sources for the two-form tensor field. And on the tensor moduli space, the unitarity of these strings requires the tension of the BPS strings, which we can compute proportional to J dot Q, must be non-negative. So we have additional positivity condition for the moduli vector J with respect to every BPS string charge Q. So string tension must be non-negative on the tensor moduli space. And furthermore, this charge Q must be sitting inside the unimodular charge lattice gamma as discussed by Cyborg and Taylor. And in F theory, these strings correspond to the D3 branes wrapping holomorphic two cycles associated with this charge Q, or which we call CI. Then this string tension positivity condition is mapped to the volume positivity condition for the holomorphic two cycles on the base. The BPS charges Q for the BPS strings form a cone called BPS cone. And this cone is dual to tensor cone, which is a cone of this moduli vector J with the tension positivity condition. And this BPS cone is generated by, BPS cone is spanned by generators, which we call CI. And so every BPS charge, since they are living inside the BPS cone, can be written as a non-negative integral sum of these generators like this. And furthermore, it turns out that moduli vector, moduli vector should satisfy this J-square positivity condition. And this implies that moduli vector must be sitting inside tensor cone. You can easily prove it. And therefore, moduli vector can also be written as a non-negative sum of the generators like this. So roughly, the BPS cone and tensor cone look like this. So in this figure, we have BPS cone generated by 6 generators, C1 to 6s, and it contains tensor cone inside. Then the moduli vector is a point along this direction, lying inside the tensor cone. So this is basic structure of the tensor cone and BPS cone. In F theory, the BPS cone corresponds to Mori cone, and tensor cone is the Kähler cone on the base. Okay, a crucial feature of these generators, BPS generators, is that they are shrinkable. So it means that we have a BPS strings for every generator, and such a BPS string can become tensionless at certain point on the tensor moduli space where the J.Ci equals 0. So in 6 dimensions, the only shrinkable or BPS strings that can become tensionless are either associative strings or little strings or critical strings. So they fall into the following 2 cases. For example, when C-square is negative, in this case, the corresponding BPS string for the generator can become tensionless at finite distance. Therefore, the BPS string must be BPS string must be related to the generators of the BPS cone of the shear piece inside supergravity. On the other hand, if C-square is C-square is 0, then it means the BPS string for the generator shrink at infinite distance. Therefore, the generator must correspond to little string or critical string inside the supergravity. So we have 2 types of generators. Indeed, since they are shrinkable, they are actually all classified. And this is the list of all generators. which we can have in the supergravity theory, and their properties are summarized in this table. And GI is the gauge algebra supported on the generators, and HI is the charged hypermultiplets. So we can extract almost all the information about these generators from this table. And using the properties of generators, we can actually understand the basic structure of the BPS cones. So for example, we can prove that two distinct generators must intersect non-negatively. This can be proven by using the mixed gauge anomaly cancellation condition when two generators support gauge algebras. In this case, this mixed gauge anomaly constraint say that the intersection number of two generators must count number of charged hypermultiplets, therefore it must be non-negative. On the other hand, if two generators doesn't support gauge algebras, which can happen only if the generator corresponds to E string, M string, or critical string. In that case, using these properties of these strings, we can easily show this fact that two generators must intersect non-negatively. And among many BPS strings, there is a distinguished class of strings which we call H string. And this H string plays very important role in our proof of the finiteness. This H string satisfies the following conditions. So first, let's say the BPS charge for the H string is F, then F square is 0, and B0F is 2. And F square equals 0 means this H string has a tensionless limit, but at infinite distance. So this H string shrink at infinite distance. In fact, we give the name H string to these strings because they are related to the critical heterotic string. More precisely, these H strings are critical heterotic strings and little strings sharing the same charge class F, satisfying these two conditions. In F theory, H strings correspond to these three branes wrapping rational fiber curve on the base B. So for example, we can consider F theory given by Hertzog surface Fn with one blow-up. Then the base can be drawn in this way. Here we have a rational fiber curve with the self-intersection 0 in this side. Then the D3 brane wrapping this fiber curve in the tensionless limit where the volume of this fiber shrink to 0 size. It provides a critical heterotic string in the duality frame. On this side, we have another rational fiber curve, but this time it's formed by two intersecting exceptional curves. Okay, yeah, Craig.
Sorry. Are you assuming that there's no algebra in the fiber above the zero curve here?
Oh, no, we can have the so in this case, so in this picture, I'm assuming there is no algebra over zero curve. In that case, we provide a critical heterotic string. But if we can consider some algebra over this zero curve, then in the tensionless limit, the string wrapping or this brane wrapping this curve provide both critical string and also little string together.
Okay, great. Thanks.
Okay, thank you for the question. Any other question? Okay, yeah, so if this brane wrap this singular rational fiber curve, then actually it provides little string. So this critical heterotic string and little string both are H string in our notation. They are sharing the same rational fiber curve F, and they become tensionless at the same time when the volume of this rational fiber curve shrink to 0 size, which occurs at infinite distance. So geometrically, these are H strings. We can extract some constraint on the bulk gauge symmetry by using the central charges of these H strings when H string exists. So central charge for the 2D or the CFT living on H string can be computed by using the anomaly inflow mechanism, and this is the result. So left moving central charge for the CFT on H string is 20, and right moving central charge is 6, and Ki is the current algebra level for the bulk gauge algebra Gi. So the level is given by intersection of the H string charge and the anomaly vector Bi associated to the bulk gauge algebra. So if Ki is positive, so if this vector Bi intersect H string, then the bulk gauge symmetry induced the current algebra on the world CFT living on H string. Then the unitarity of this world CFT on H string requires the following inequality. So each current algebra contributed to the central charge, and the central charge contribution from the current algebra can be read off from the Bess-Zumino model for the Kang-Moody algebra, and this is the result. Then some of these current central charge contribution from each current algebra must be less than or equal to left moving central charge. So this is 20 in this case. And from this inequality, you can actually extract the bound on the gauge algebra with positive Ki. So the rank of gauge algebra with positive Ki is bounded by 20. And we call such gauge algebra with positive Ki with respect to the H string as external gauge algebra. So rank of the external gauge algebra is bounded by 20. In this geometric example, we can consider several gauge algebras on different curves, but here the gauge algebra G1 and curve supporting this gauge algebra G1 and another curve for G2, they intersect this rational fiber curve. So rank of gauge algebra G1 and G2 is bounded by 20. Okay, so we have this rank bound for the gauge algebra supported on the curve intersecting the rational fiber curve. Now, I'll prove that for every 60 supergravity theory, 1-0 supergravity theory, we must have H string in the BPS charge spectrum, except a few exceptional cases, which I'll explain later. So to show this existence of H string in the charge spectrum, I'll use the properties of the generator Ci, and also another property for this vector, anomaly vector V0. And from classification, we can read off the intersection between this anomaly vector V0 and generator Ci, and this is the result. And as you see, only H string and also generator with the self-intersection -1, they intersect positively with V0. And now recall the positivity condition, which I explained at the beginning of this talk, related to this charge V0. So J dot V0 must be non-negative. This was one of the positivity condition I explained. And also, since J is living inside the tensor cone, so it can be written as a non-negative sum of the generators. And this condition should hold everywhere in the tensor moduli space. So if we combine this positive condition together with this intersection, now you understand the Shikti theory must contain H string or -1 generator or both. Otherwise, you cannot satisfy this condition with this expression of the moduli vector J. Now we define a projection to a subspace of the tensor moduli space, which is orthogonal to all -1 generators. And this projection is called blot down, defined in this way. And it turns out that after blot down, the BPS cone is also projected to the subspace, which doesn't contain any -1 generators. But this positivity condition should hold everywhere in the tensor moduli space, including the subspace after the projection. But after projection, we don't have -1 generator. Therefore, this positivity condition, together with this intersection number, prove that there must be H string in the BPS spectrum in the Shikti supergravity theory. Okay. But there are two exceptions. First case is when T is 0. So if there is no tensor multiply, then it means we don't have tensor moduli space. So our argument doesn't apply. So in this case, we don't need to have H string. Second exception is when B0 is 0. In this case, this positivity condition is trivially satisfied without having H string. So except these two cases, we should have H string in the Shikti supergravity. In geometry, this corresponds to the case when base is given by P2, and second case corresponds to when the base is given by any guess surface. In fact, this second case can occur only when T is number of tensor is 9. So, except these two cases with a small number of tensors, we proved that the Shikti theory must contain H string in its BPS spectrum. Indeed, in geometry, except these two basic cases, all other bases contains the rational fiber curve. It's proven in geometry. So our proof for the field theory agrees with the geometrically known fact. Okay, I will explain one more non-trivial property of the H string. There is actually containment relation between the SCFTs and H strings. So we claim that BPS strings with charge Q satisfying the following two conditions must be element of the little string theory for the H string. So firstly, if Q is orthogonal to H string, and secondly, if the gauge algebra GI supported on this Q is not of small type, then we claim such BPS string and the BPS charge Q must be component of the little string theory of the H string. Here G small means empty, so no gauge algebra, or SU234, or SP2, or G2. So if this charge Q two conditions, we are claiming that there is a containment relation of the BPS string for the charge Q and the little string theory. We can prove this by using the following two properties. Firstly, whenever H string shrink, which occurs at infinite distance, Q string also shrink. And this property follows from this orthogonality condition. And secondly, the intersections of this charge Q with any other null charge is finite if the gauge algebra GI is not of small type. So using these two properties, we can show this containment relation, but I'll not explain the details. So if you are interested in the detail, then please ask me later after this talk. Okay, before going into the proof of the finiteness, let me summarize the key ingredient we will use. So far we have shown the following three properties. Firstly, two generators must intersect non-negatively. Secondly, we have a H string in the BPS spectrum of the supergravity theory. And thirdly, we have a containment relation for the orthogonal charge Ci. And it turns out that we have very hard time to prove these three properties in generic effective field theory, but it turns out that these three properties are rather trivial or easy to prove in geometry. So in geometry, these three properties are kind of obvious statements. But we need one more ingredient or two more ingredients. First one is the gravitational anomaly cancellation condition, which states that every component in the supergravity theory contributed to the gravitational anomaly, and their sum must be 273. But quite surprisingly, I found that there is no counterpart to this gravitational anomaly constraint in geometry at this moment. There are some effort to understand this gravitational anomaly cancellation condition from the all the characteristics of the Calabi threefold as discussed in these papers, but their argument does not apply for the generic cases. So it's quite interesting that this gravitational anomaly cancellation condition, which is kind of trivial in field theory, is not established in geometry at this moment. And the last ingredient is the classification of Schicht SCFTs and little string theories. So combining these 5 ingredients, now we will show the number of massless fields in Schicht supergravity theory is finite. Any question? Okay. Then I'll show you. I will show you how to prove the finiteness of the number of tensors first. So for this, I'll employ the gravitational anomaly constraint. So as I said, all the gravitational anomaly contribution coming from the component in the supergravity theory must be 273, and each contribution is given by the number of hyper minus number of vector plus 29 times the number of tensors for every component. And there is a very interesting observation discovered in this paper, and they found that among the components in the supergravity theory, the only component that have negative contribution to this gravitational anomaly SCFT atoms of charge Q with negative self-intersection. And more precisely, these atoms have a Q scale -5, -6, -7, -8, and -12. And they support only exceptional gauge algebra such as F4, E6, 7, and E8. apart from these 8 SCFT atoms, all the other components contribute in the supergravity theory, contribute positively to the gravitational anomaly cancellation condition. And this can be easily understood through this gauge anomaly cancellation condition. So recall this anomaly cancellation condition. So for every gauge algebra, we have an associated tensor multiplet, and each charge Q square should satisfy this condition. Then as you see, if Q square is big, it requires to have more hypermultiplet than the vector multiplet. But if you look at the anomaly cancellation condition, then the anomaly contribution from each component is given by number of hyper minus number of vectors. So in order to have a negative contribution to the gravitational anomaly, you can see Q square must be small enough. Okay, otherwise the number of hypermultiplet will exceed number of vector multiplets so that we have the positive contribution to the gravitational anomaly. So it turns out that only these 8 SCFT atoms can have negative contribution to the gravitational anomaly. Therefore, in order to have arbitrarily large number of tensor multiplets, since we have this gravitational anomaly cancellation condition, we need infinite number of these SCFT atoms. Okay. And these atoms fall into the following 2 categories. Firstly, it can intersect to the charge of the H string, or it could be orthogonal to the H string. In the first case, as I explained, the unitarity of the BPS string on this H string requires this inequality. So rank of gauge algebra is bounded by 20. So number of these atoms have negative contribution to the gravitational anomaly. In this first case, is finite. In the second case, since it's orthogonal to the H string, and also gauge algebra here are not of the small type, we have a containment relation. So this charge Q must be component of the little string theory of the H string. So the BPS string for this charge Q should be component of the little string theory of the H string. So in this case, we can use the classification of the little string theory and understand more properties of this charge Q or these SCFT atoms. And we found quite remarkable result. So from the classification of the little string theory for the H string, it turns out that whenever we embed these atoms, they are not coming alone. They are always accompanied by additional methods. And if you take into account the contribution from these additional methods, then the total gravitational anomaly contribution, which includes this negative contribution from these atoms, together with additional contribution from these extra methods inside the little string theory, eventually provide positive contribution to the gravitational anomaly. So in the second case, all these atoms, together with the additional methods, have at the end the positive contribution to the gravitational anomaly. Therefore, number of these atoms is again finite because the gravitational anomaly constraint. So to understand this, I have a brief review on the classification of these SCFTs and little string theories. So SCFT, 60 SCFTs and little string theories are classified in these papers about already 10 years ago. And they found that these theories are essentially generalized quiver theories with the tensor base of this shape. So base of the tensor multiplet is given by this tree-shaped quiver diagram, and it consists of nodes and the link. So as you see, every node is connected by link, and node is nothing but a single tensor multiplet with the self-intersection -4, 6, 7 up to -12. And link is a finite chain of the tensors with the self-intersection -1 to 3 and -5. But crucial feature here is that whenever we have node, they can be connected to each other only by link. Okay, so node and link, they always come together. So they form a kind of quiver diagram. In this talk, we are interested in only the little string theories associated to H string. And these little string theories are classified in these papers. And what we found is that the little string theories related to H string can have only p-type endpoint. So they have only very special endpoint. And p-type endpoint means you can blow down all -1 tensor multiplets inside the little string series. Then at the end, you will have the just single tensor multiplet with the charge F satisfying these H string conditions. So the little string series, which can realize the H string, is quite constrained. And also, in particular, the base of this little string theory having p-type endpoint has very special topology, which doesn't contain any loop. So in the base, we don't have any loop for the series with the p-type endpoint. Furthermore, it turns out that these little string series for H string cannot include any frozen singularities. So the little string series, including frozen singularities, are classified in this paper. And you open this classification and try to read what kind of configuration we can have. And we found that no frozen singularity sitting inside the little string theory for H string. Okay. So it means the gauge group GI associated to the frozen singularity must be external. It means the charge Q supporting this gauge group G for the frozen singularity must intersect the H string. So for example, gauge algebra SUN with the symmetric hypermultiplet can be realized with the frozen singularity. Then this gauge algebra must be external. Since it's external, rank of this gauge algebra is bounded by 20. So rank of gauge algebra associated to the frozen singularity is bounded by 20. So this answers to the question by Eden. Okay. And also, abelian gauge groups cannot be sitting inside the little string theory for the H string. So all the abelian gauge groups must be external. So their rank is again bounded by 20. The number of tensor bigger than 0. So if we have tensor moduli space in supergravity theory, rank of abelian factors is bounded by 20. And similar bound was discussed in this paper, but our bound is stronger than their bound. Any question about this? Okay. And in particular, interior link that connect two nodes in the middle. So in the middle, we have the node. They are all connected by a methods are very special 6D associative, describing the physics of M5 rings proving singularities in M theory. And these conformal methods are classified in this paper. So for example, so these are E-type conformal methods, and they describe the M5 rings on E-type singularities. And from this conformal method, so this is the combination of E-type conformal method together with the adjacent node. And from this classification data, you can read out their gravitational anomaly contribution. And we compute it. And all these E-type conformal methods together with adjacent node contribute positively to the gravitational anomaly. So their contribution is always 30. This implies that we cannot have arbitrary large number of these E-type conformal methods connecting the node with the E-type gauge algebras. So in the middle, we cannot have arbitrary large number of these conformal methods and E-type nodes or nodes with the E-type gauge algebras. So number of these combination is finite. And also, you can see, as I explained, every node comes with a link. And what we found is that their combination always contributes positively to the gravitational anomaly, roughly bigger than or equal to 30. So therefore, every component in the little string theory for the H string has positive contribution to the gravitational anomaly. So we can have negative contributing SCFT atoms to the gravitational anomaly, but they fall into the following two categories. But in the first case, because the rank bound, number of these negatively contributing atoms is finite. But in the second case, their gravitational anomaly contribution is positive. So this gravitational anomaly constraint implies that number of these atoms is again finite. So this proves that number of tensor multiplet in Shakti supergravity theory is finite. Okay. So T is finite. And with some more effort, you can also show that number of vectors and number of hypermultiplets are finite, but I'll not explain the details. And together, this establishes the number of massless fields in Shakti supergravity theory is finite. Okay, and we can go further and compute the exact bound on the number of tensors and rank of gauge algebras. And the idea to compute these bounds is very straightforward. So we have two steps. We first identify the composition of atoms for the little string theory of H string, such that it can host large number of tensors and higher rank of the gauge algebras. So we'll first determine the configuration for these little string theories for the H string. Then we add external methods here and here or more properly, such that all the anomaly constraint and also rank bound are satisfied, and construct the supergravity theory that contains the maximum number of tensors and highest rank of gauge algebras. And this can be performed quite systematically. But the computation is rather technical, so I'll summarize just the key result. So let me first compute the bound on the number of tensors. For this, what we found is that among the components of the little string theory for the H string, this EA conformal method attached to the -12 tensor node supporting EA gauge algebra has maximum tensor to anomaly ratio. So T over delta is maximal for this combination, this component in the little string theory. It contains 12 tensor multiplets, and it minimally contributes to the gravitational anomaly, which is 30. So our strategy to build maximal tensor theory is to embed this component as many as possible into a single little string theory for the H string, and complete it by adding external methods to the supergravity theory. So we prepare a large number of these components together with the additional methods and form a supergravity theory. And this is the solution. So this is the maximal tensor supergravity theory we can construct while maintaining all the constraints we found. And this supergravity theory contains a single little string theory for the H string, consisting of 16 EA times EA conformal methods, together with the 2 strings here and here. Oh, sorry. And this H string intersects 2 external tensor multiplets here and here with EA gauge algebras. And in total, they form a supergravity theory. And number of tensor in this theory is 193, and rank of gauge algebra is this big. We found that this is the maximal tensor theory we can construct in Shakti supergravity theory. So we have tensor bound, which is 193. Okay, lastly, let me compute the bound on the rank of gauge algebras. It's more involved, but what we found is that only the following 9 semi-classical configurations, which has only semi-classical gauge algebras over all the tensor multiplets, can realize higher rank little string theories. So we have 9 base configurations, and each tensor multiplet in this configuration supports only classical gauge algebras, such as SU, SP, and SO gauge algebras, and they are connected by fundamental hypermultiplets. So for this given little string configuration, we add the external methods to form the supergravity theory. And to compute the maximum rank theory, we actually perform a numerical optimization for each given 9 semi-classical configuration with some assigned SO, SP, SU gauge algebras. And at the end of this numerical optimization, we found this solution. So this solution contains the maximum rank gauge algebra in the Shakti supergravity theory. And this theory consists of a single little string theory having affine E-type tensor base supporting SO and SP gauge algebras. And this H string intersects a single external tensor multiplet with a self-intersection -4 supporting SO32 gauge algebra. And this theory contains 9 tensor multiplets, and rank of gauge algebra is 480. And this is the maximal tensor theory we can construct in Shakti. So bound on the rank of gauge algebra is 408. Furthermore, we found that these maximal theories can be realized in string theory. They are theories living on 24 instantons on EA times EA and associated to heterotic string compactified on K3 with EA singularity. These theories are investigated in these papers. And furthermore, it turns out that if you circle compactify these theories, these two theories are trivial to each other. So this result, saying that two maximal theories we discovered from the field theory are realized by string theory, provide very non-trivial evidence for the string Lampos principle. And lastly, we found that these two theories have a geometry realization in F theory. So for example, Tmax theory corresponded to an elliptic threefold over the base B given by Hertzsprung surface F12 with 192 blobs. And this threefold had these Hatch numbers. And maximal rank theory is associated to another elliptic threefold over the base given by F4 with an 8-point blob. And it has these Hatch numbers. So they both have corresponding elliptic threefold. And our result predict a sharp bound on the Hatch numbers of the elliptic threefold. So firstly, the H11 of the threefold is bounded by 491, and this bound is saturated by these two geometries. And H11 of the base is bounded by 194, and this bound is saturated by this Tmax theory. And also in this Hatch number list from the Calavia, for the Calavia threefold in Calavia database, these two geometries corresponded to this very corner at this point. So our result predicts that there would be no more Hatch number in this list along this direction for the elliptic Calavia threefold. Okay, let me summarize. So I have shown that all shifted supergravity theory has bounded number of tensors and rank of gauge algebras. So we have a number of, we found the number of tensors and rank of gauge algebra both bounded. And our argument is based on the physics on the tensor moduli space and unitarity of the VPS strings. And in particular, we use the classification of SCFTs and little string theories. And our result predict the sharp bound on the Hatch numbers of the elliptic threefold. And we have shown that explicit geometry saturates this bound. So this provides another evidence for the string Lampos principle. Then we can ask the following questions. So is the number of allowed shifted supergravity theory finite? So I have shown that number of massless field is finite, but I haven't proven that number of theory is also finite. So this is an interesting open question. And second question would be the generalization to lower dimensions and lower supersymmetric cases. Okay, let me stop here. Thank you very much.